Hi, welcome back to this channel. In this video, we're going to learn about the nucleophilic substitution that always happen in the haloalkanes. And then there are two types of mechanism, which is Sn1, Sn2. And then we need to show the mechanism. And then we have last, we need to compare the reactivities of primary, secondary, and tertiary haloalkane towards hydrolysis and alcoholysis. One of the main reactions that carried out by haloalkane is nucleophilic substitution reaction. As we know that the bond between the carbon and halogen is a polar bond, so that the halogen is nucleophile, so later it will replace by the nucleophile. So that's why this reaction is known as nucleophilic substitution reaction. However, for the second type of reaction, which is the elimination, dehydrohalogenation, basically we already learned in chapter alkene, when the haloalkane undergo dehydrohalogenation will produce alkene, and then we need to base on the Say-Jeff rules to consider which is the major and minor product. Besides that, we also need to consider is that any rearrangement may happen. Okay, as we know that haloalkane will undergo nucleophilic substitution reaction. So there is two types of nucleophile. One is considered strong nucleophile and weak nucleophile is another type. So basically you will notice that the strong nucleophile always come with the ion, while the weak nucleophile are the neutral A molecule. So now we have to look at the first one. NaOH is considered as strong nucleophile because it will always produce Na plus and OH negative. So in the haloalkane, the Cl is the halogen is the nucleophile. So in the NaOH, the OH will consider the nucleophile. So that's why you can see the chlorine is replaced by the OH. So next, if we have the NH3 ammonia, this one is weak nucleophile, which the bond will break between hydrogen and NH2. So as we know, nitrogen is one of the most electronegative element, and hydrogen always is the most positive element. So we can see that the Cl replaced by the NH2. KCN will produce K plus and Cn negative, so Cn will be replace the halogen. So to keep in mind that here you have to remember that if the haloalkane react with the KCN, there will have one more carbon atom. Next one is the CH3O and N, so we will produce CH3O negative and Na plus. So basically at this moment now here, as long as we can see that there is Na plus, for example like this, Na plus, K plus, Na plus, and Na, basically all these are strong nucleophile. So because of CO negative is the partially negative, so that's why if you look at here, the nucleophile is OCH3. When this happens, CH3, CH2OH, so the bond will break between the oxygen and hydrogen. As we know again, hydrogen is always most electropositive. Therefore, the CH2O will be partially negative and will replace the halogen. So for the last one, CH3, CH2, COO negative and Na plus. So the CH3, CH2, COO negative will replace the Cl. So in this slide, try to remember all the 1, 2, 3, 4, 5, and 6 reagent that can undergo nucleophilic substitution when react with the haloalkane. And again, the nucleophile we need to classify strong nucleophile and weak nucleophile. Generally, strong nucleophile is with the negative charge, while the weak nucleophile generally is the neutral molecule. So based on the formula, as long as you can see that there is Na plus and K plus, so means that the partner will be negatively charged. So they will become the strong nucleophile. Okay, at the same time, we answer tutorial question number 3 and then also fulfill the requirement of the learning objective, explain Sn1 and Sn2. So what is meant by Sn1? Basically, it means unimolecular nucleophilic substitution. So basically, uni means the one. Okay, so in other words, to say it is also first order reaction, and where in the mechanism later in the slow step, you will only involve the haloalkane. So Sn1 only have one step mechanism. Carbocation ion will be the intermediate. And then due to the formation of carbocation ion, there is possibility to do rearrangement. Again, because of the carbocation ion might be formed, so tertiary carbocation ion is the most stable. So from here that we know that however, benzylic carbocation ion is more stable than tertiary carbocation ion. So the reactivity will increase from the methyl halide primary, secondary, tertiary, and the most reactive towards Sn1 will be the benzylic carbocation ion, and always will involve the weak nucleophile. However, the Sn2 is totally opposite side with the Sn1. Sn2 is the second order reaction, which will involve the haloalkane and also nucleophilic. The nucleophile involve one-step mechanism, no carbocation ion, so rearrangement is impossible, and the most reactive class of haloalkane toward Sn2 is methyl halide, and that will involve the strong nucleophile. Very quickly, let's look at the mechanism for Sn1 and Sn2. So we focus on Sn1. If you still remember, just now we say it will be unimolecular unimolecule nucleophilic substitution. So what is the meaning of uni? Means that it's referred to one. So you can see over here there is one molecule at the reactant as the reactant in the step 1, and the step is slow step. So the bond between carbon and chlorine will break heterolytic because chlorine is more electronegative, and then it will form carbocation ion. Since this is the tertiary carbocation ion, so no rearrangement will be happen. So and then step 2, and where also mentioned more than one step. Okay, and then step 1 always involve the one type of molecule. So this is a first order reaction. So then the nucleophile, which is the water, will attack the carbocation ion to form a compound with the positive charge, and then the water again will go and attack the hydrogen. The bond will break down heterolytic and form alcohol with the H3O+. So Sn2 is bimolecular nucleophilic substitution. So bi means 2. So when you look at the step 1, you will involve 2 reactants. One is hydroxide, which is the nucleophile, and another one is the haloalkane. So at the same time, you also notice here with the nucleophile is with the negative charge, so it's strong nucleophile. While for the Sn1, recall back here, we can see the H2O, which is neutral nucleophile, so it is considered weak nucleophile. Okay, so when attacked, we will produce a activated complex, so that with very fast, the product will be formed, and Cl negative is the kick out nucleophile. So again, from here we can see that the reaction is the mechanism is involved one step. Learning objective D, we need to compare the relative reactivities of different classes of haloalkane towards hydrolysis, which means it will react with water, or alcoholysis means that it will react with alcohol. So arrange the following compound in order of increasing reactivity towards Sn1. So we know that this is the secondary haloalkane, this is primary haloalkane, and this is tertiary haloalkane. So as we know that if we look at the Sn1, means that it will involve one molecule in step 1. So and then it will form the carbocation ion. So we know that tertiary carbocation ion is most stable among these 3 classes of carbocation ion. So C, okay, let's say this is A, B, and C. So we want to arrange in order of increasing reactivity. So C is the most reactive, follow the second reactive is the A, and B is the least reactive towards Sn1. Okay, so we write down increasing reactivity towards Sn1. So now we need to do the explanation. So you can mention that the factors affect reactivities of haloalkane towards Sn1 is stability of carbocation ion. Okay, therefore C, which is the tertiary haloalkane with 3 alkyl group, is most reactive towards Sn1. Question number 5. Which compound below give the fastest Sn2 reaction with sodium methoxide? So sodium methoxide is NaOCH3. Why we call sodium? Because we have Na. Why is methoxide? Because we have methyl group attached with the oxygen. So when have oxygen, always end with oxide. One carbon is met, so that's why this NaOCH3 is known as sodium methoxide. And then explain. So 1-bromohexane is primary haloalkane. 1-bromo-2,2-dimethyl also primary haloalkane. So hexane with 6 carbon, and then 1 bromine at the first carbon. So complete with CH3, CH2, 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 and this one also CH2. while 1-bromo, 2,2-dimethyl butane. Butane is the parent name. So 2-methyl, 2,2-dimethyl, 1-bromo. So here CH2, CH2, CH3. So as we already know that if Sn1 tertiary is the most reactive, in Sn2 primary is the most reactive. So now both haloalkane are primary haloalkane. So we will continue with the second factor that we need to consider, which is the steric effect. So basically the steric effect is look at the bulky group. Okay, so for this one, it even have more carbon, but the arrangement is considered straight chain. But if for this one with tertiary group, so this one we will consider as bulky group. So if bulky group means that they have larger steric effect. So if have larger steric effect, will less reactive towards Sn2. So now, which compound gives the fastest rate toward Sn2? So the answer is 1-bromohexane. So if want to mention, I think basically we already write it down. So you have to mention that the 1-bromohexane show less steric effect, which make the nucleophile easier to attack the alpha carbon in 1-bromohexane. Okay, so now what is the meaning of alpha carbon here? So alpha carbon, basically we can classify as carbon that attach to halogen, okay, or is attached to the functional group that we want to study. Therefore, this one is the alpha carbon and another one alpha carbon is over here. So if we want to attack, so if you see the word attack, okay, so means that we have to attack from the back. So if you attack from the back, okay, attack from the back, so here we consider back. So this is bulky group will hidden the alpha carbon, okay, bulky group, okay, in other words to say alpha carbon is hidden, so difficult to attack the alpha carbon. Okay, question number 7. State and write the mechanism for each of the following reactions. So we look at A. Before we write the mechanism, we need to identify the type of mechanism, whether it's Sn1 or Sn2. So again, before we can decide, we have to check the haloalkane. So this haloalkane is tertiary haloalkane, and the product here is tertiary alcohol. So basically, as we already go through just now, the difference between Sn1 and Sn2, tertiary haloalkane is most reactive toward Sn1. So basically means that for 7A, Sn1 mechanism will be happen. So then now we need to look at the mechanism, the working step for the mechanism. So step number 1, okay, this is step 1. Okay, we have the bond between carbon and bromine will break down heterolytic in a slow step, then produce tertiary carbocation. So then the water, which is the weak nucleophile, will attack the carbocation and then forming the OH2 plus. Next, this will be the step 2. Okay, attack of nucleophile on carbocation. Then step 3 is deprotonation. So one of the water molecule will the oxygen in the molecule, the lone pair electron in the oxygen will donate to hydrogen, and then the bond will break between oxygen and hydrogen heterolytic, which later will have the oxygen will have 2 lone pair electron to form tertiary haloalkane, and we get back the acid condition H3O+. Question B. CH3CH2Cl is primary haloalkane. OH negative is strong nucleophile. So when we have primary haloalkane with strong nucleophile, we'll prefer Sn2. So Sn2 is a one-step mechanism, and then at the initial part of the mechanism always involve 2 molecules, which is the OH negative. So basically the OH negative will have 3 lone pair electrons. One of the lone pair electron will attack the carbon from the back. So make the bond between carbon and chlorine will break down heterolytic. This is a slow step. And then here we will have a transition state, which this is the activated complex. So this activated complex will have 5 bonds, and where the bonding between the OH and the Cl is the temporary bond. Okay, then do keep in mind that the symbol at here is to show that it is the transition state with the presence of activated complex. Okay, then the Cl negative will be kicked out and replaced by the OH negative. So at the same time, you will notice that the configuration of the configuration means that the way you draw the structure is different for the reactant and product. So we will discuss further during the tutorial time. Question 7c. So when you look at here, this is the primary haloalkane. When you see the NaOH, you will notice that this is the strong nucleophile because consists of Na+. So and then produce a primary alcohol, and then also the tertiary alcohol. And then here they mention that this tertiary alcohol is the major product. So here maybe you have to highlight primary haloalkane, end up we get tertiary alcohol as the product, as the major product. So we know that rearrangement happen. Okay, if from primary to tertiary means that there is rearrangement occur. So as usual, step 1, the bond between carbon and iodine, which is the halogen, will break down heterolytic. Slow step at where Sn1 will involve one reactant in the step 1, which will produce the carbocation. This carbocation is primary carbocation, and then will shift with the hydrogen here. So we label here 1,2 hydride shift with the reversible arrow, and then to form the tertiary carbocation. Okay, so the rearrangement also under step 1. So step 2, the water, because of the aqueous solution, the water will attack the tertiary carbocation ion by giving one lone pair electron to the carbocation ion. Then the oxygen now will become 3 bonds with one lone pair, so that's why it is positively charged. Then step number 3 will undergo deprotonation. The lone pair electron of the oxygen from the water will attack the hydrogen, and then the bond will break down heterolytic again, and up we will have the oxygen will have 2 lone pair electron, and the side product is the H3O+. Okay, now let's look at the question to decide whether the nucleophile given in the question is strong nucleophile or weak nucleophile, and then we are going to carry out Sn1 or Sn2. Look at the first one. The haloalkane is primary haloalkane, and NaOH is the strong nucleophile, and then produce primary alcohol. So primary with strong nucleophile means that will undergo Sn2. Next one, primary haloalkane, and then with water, which is the weak nucleophile, and then form tertiary alcohol. So from primary become tertiary, we know that rearrangement occurs, so Sn1 is carried out. Third equation, secondary haloalkane, CH3OH is weak nucleophile. So secondary with weak nucleophile, so we focus on because means that secondary is in the middle towards the Sn1 and Sn2. So in this case, we will depend on the type of nucleophile. Since it is weak nucleophile, so prefer Sn1. Next one is the secondary haloalkane with strong nucleophile, and then again there is no rearrangement, so you have to use Sn2 for the mechanism. So next one is primary haloalkane react with weak nucleophile with tertiary product. So means that there is rearrangement and involve Sn1. Next one again, primary with the weak nucleophile because no charge, or generally we can say that we didn't see Na+ and K+. So we'll produce a tertiary product. So again, there is rearrangement. So the reaction is Sn1. Last question, primary haloalkane, and then produce a primary product with strong nucleophile because we can see here is the Na+. So have to carry out Sn2 mechanism. Okay, so with this video, I hope you roughly have the idea what's the difference between Sn1 and Sn2, how you know the nucleophile is strong nucleophile or weak nucleophile, and then based on the class of the haloalkane, you will be able to determine whether the compound or the haloalkane undergo Sn1 or Sn2. If they are secondary haloalkane, basically will depend on the type of nucleophile. If primary haloalkane there is 2 conditions, they might carry out Sn1. If there is rearrangement, they will maintain as primary product, so means that they will undergo Sn2. Okay, so that's all for this video. So for the mechanism, we will discuss further during the tutorial time. So in next video, we will discuss another type of reaction that might carry out by the haloalkane. See you in next video. Bye bye.